Cambridge Assessment Admission Testing, 6th Term Examination Paper, STEP. 2019 Paper 1, Mathematics 1, Code number 9465, Section A. The link to the question paper is in the description below. Hi, I am Babak. In this video I am going to solve question number 7 from this past paper. Let me read the question for you first. Consider the following steps and prove that square root of 2 plus square root of 3 is irrational. Number 1. If an integer a is not divisible by 3, then a equals to 3k plus or minus 1 for some integer k. In both cases, a squared is 1 more than a multiple of 3. Number 2. Suppose that square root of 2 plus square root of 3 is rational and equal to a over b, where a and b are positive integers with no common factor greater than 1. Number 3. Then a to the 4 plus b to the 4 equals to 10 times a squared times b squared. Number 4. So if a is divisible by 3, then b is divisible by 3. Number 5. Hence, square root of 2 plus square root of 3 is irrational. Part 1 of the question. Show clearly that steps 1, 2, 3, and 4 are all valid and that the conclusion 5 follows from the previous steps of the argument. Part 2 of the question. Prove by means of a similar method but using divisibility by 5 instead of 3 that the square root of 6 plus a square root of 7 is irrational. Why can divisibility by 3 not be used in this case? I recommend you to pause the video at this point and give the problem a try yourself, and then come back and replay the video to compare your solution with my solution. Okay, so in the first part of this problem, we're supposed to show that the statements 1, 3, and 4 are indeed valid, and then of course use these statements to show that the statement 5 is also valid, meaning that square root of 2 plus square root of 3 is an irrational number. Okay, let us focus on statement 1 first. A is an integer which is not divisible by 3. We are supposed to show that a equals to 3 times k plus or minus 1, where k is an integer. So we want to show that if a is not divisible by 3, then a can be written as a integer multiple of 3 plus or minus 1. To prove this part of the problem, I just want to remind you about a famous and fundamental theorem in number theory, which is called the division algorithm. Yes, the division algorithm. So what is the content of the division algorithm? I just want to recall you about that. Division algorithm asserts that if n is an integer and if m is a natural number like 1, 2, 3, 4, etc., then there exists a unique integer q. So this reverted e is actually, it means there exists, and this exclamation mark emphasizes that this is unique. So this means that there exists a unique q in the set of integers, and there also exists an integer r such that n can be written as m times q plus r, where r lies in this interval greater than or equal to 0, strictly less than m. So this is the assertion in the division algorithm. Okay, now in this statement number 1 I have an integer. So let me do this in the division algorithm. Let me replace n with our integer a, and let me replace m with 3. Then what does it mean? This means that a is equal to, instead of m in the division algorithm I put 3, so it becomes 3q plus r. But we also know that r lies in this interval greater than or equal to 0, smaller than m. But in this case, m, I have replaced m with 3, so this becomes 3. Yes. So this means that for any integer a can be written as 3 times an integer plus a number lying between 0 and 3. But of course, we know that r is between 0 and 3. We also know that r is an integer, so this implies that there are 3 possibilities for r. One of them is 0, the other one is 1, and the final one is 2. Yes? Okay, so if r is equal to 0, what happens? Instead of r here, I put 0, then I immediately get that a is equal to 3 times q. So it means that a is a multiple of 3. If r is equal to 1, then what happens? I will get a is equal to 3q plus 1. Yes, so I have replaced this r here with 1. I get this. And finally, if I put r equal to 2, I will get a equals to 3q plus 2. Yes, so it means that in general any integer a can take one of these, and exactly one of these forms. Yes, either it is multiple of 3, or it's multiple of 3 plus 1, or it's multiple of 3 plus 2. Yes, of course in this statement a is assumed to be not divisible by 3. So if a is not divisible by 3, so this is actually ruled out. This is not happening here. Yes, so here this is not the case here. Since a is assumed not to be divisible by 3. Yes, so this cannot happen in principle. So it might happen that this happens, which is good. It means that a is an integer multiple of 3 plus 1. But this one is multiple of 3 plus 2. Okay, but this can be simply modified. How? I can write it as 3q. Instead of 2, I can write 3 minus 1. Between the first two terms, I can factor 3 out. Then I will have q plus 1. And then I will have minus 1. Okay? But we know that this q is an integer. So q plus 1 is also an integer. So I can call it, for example, I can denote q plus 1 by a letter k. Then it becomes 3k minus 1. Yes? So let us see what happens. If a is not divisible by 3, this is ruled out. So there are 2 possibilities left. Either a is an integer multiple of 3 plus 1, or a is an integer multiple of 3 minus 1. So actually we were able to show that this is indeed the case, and then we showed that statement 1 is indeed valid if a is not divisible by 3. Yes. Okay, now we are supposed to prove statement number 3. We are supposed to show this equality. But what are A and B? It's clear, it's mentioned in statement number 2. The goal of this problem is to prove that this is irrational. In statement number 2, we suppose on the contrary that square root of 2 plus square root of 3 is rational. So it can be written as a fraction whose numerator and denominator are integers. Okay, and then we are supposed to show this. Okay, so what does it mean? It means that we know that square root of 2 plus square root of 3 is a over b. We are supposed to prove that a to the 4 plus b to the 4 is 10a squared b squared. This is what we want to show. Okay, if you look at what we are going to show, you see that there is no square sign involved. Yes, so this is good. This gives you the hint how to do the problem. We need to get rid of these square root signs. Yes, to get rid of square root signs, the natural step is to raise to power 2. Okay, so I raise this expression, both sides of this expression, to power 2. So this becomes square root of 2 plus square root of 3 to the power of 2. On the right hand side I will have this. Okay, I expand the left hand side. The first one to the 2 plus 2 times the first one times the second one and plus the second one to the 2. And then I will have a squared over b squared on the right hand side. Okay, now 2 plus 3 is 5. I move 5 to the right hand side. Then I will get 2 square root of 6 is equal to a squared over b squared minus 5. Okay, so still a square root is left. I need to get rid of that one as well, so I raise both sides to power 2 once more. Yeah, so what I get, the left hand side to the power of 2 is 4 times 6, which is 24, and the right hand side becomes a squared over b squared minus 5 to the 2. So then I can expand the right hand side. It becomes the first one to the 2, 2 times the first one times the second one, and finally the second one to the 2. Okay, so at least this is good because you don't see any square root signs involved anymore. But this, I want to manipulate this a little bit algebraically to reach to this. It's easy. I multiply both sides by b to the 4. I don't have any fractions. So this becomes 24b to the 4. On the right hand side I will have a4 minus 10a squared b squared, and then finally 25b to the 4. Now my goal is to move this term to the left hand side. It becomes positive. Move this one to the right, it becomes negative 24b4, and then I will have a positive 25b4 here, so it becomes b4. So what I get is that this is 10a squared b squared is equal to a to the 4 plus b to the 4. And that is exactly what we are supposed to prove in the statement number 3. Yes, that's exactly that expression that we are supposed to prove. Okay, now we want to prove statement number 4. Statement number 4 reads like this. A is divisible by 3. We want to prove that B is also divisible by 3. Of course, A and B are the same A and B that fulfill this relation. Okay, let me introduce you a symbol here. I'm completely sure that you know about it, but let me write it here with a different color. So when x and y, non-zero integers, okay, we write x and then we put this vertical line and then write y and read it x divides y. If and only if y is divisible by x. Okay, so it's easier to use this notation here. Okay, now here in this statement, Number 4, we know that A is divisible by 3. We want to prove that B is also divisible by 3. So what does it mean? It means that we know that 3 divides A. We want to prove that 3 also divides B. Yes? So how can we prove that? I want to prove this by contradiction. So I would say that assume that this is not the case. Assume that this is not the case, and 3 does not divide B, or B is not divisible by 3. Then, according to the first statement, we know that B is equal to 3k plus or minus 1 for some integer k. Yes? Okay, this means that B is 3 times k plus or minus 1. So this means that B is congruent to plus or minus 1 modulo 3. Okay? And then it means that B to the 2 is congruent to plus or minus 1 to the 2 modulo 3, but plus or minus 1 to the power of 2 is just 1. So this implies that B to the 2 is congruent to 1 modulo 3. And then if I raise this to power 2 once more, then I will get that B to the 4 is also congruent to 1 modulo 3. Yes, so both B2 and B3, B2 and B4 are congruent to 1 modulo 3. Yes, okay, but we also know that 3 divides A. Yes, so when 3 divides A, what does it mean? When 3 divides A, it means that A is congruent to 0 modulo 3. So this means that A to power 2 is also congruent to 0 modulo 3. Okay, so remember these things. I need to go to the next page now. So what we have? We have 3 divides A, so this means that A is congruent to 0 modulo 3. So this means that A squared is also congruent to 0 modulo 3. And if I multiply both sides of this expression by 10b squared, then it becomes 10a squared b squared is congruent to 0 again modulo 3. This is on the one hand. On the other hand, we learn that from here we can also learn that a to the 4 is congruent to 0 modulo 3 by raising both sides to power 2. And if you remember from the last statement here b4 is also congruent to 1 modulo 3, so then I can write it next to it, and we know that b to the 4 is congruent to 1 modulo 3. So if I add both sides together, then a4 plus b4 is congruent to 0 plus 1 modulo 3. So then it means that a to the 4 plus b to the 4 is congruent to 1 modulo 3. Yes? But on the other hand, we know that a4 plus b4 is equal to 10a squared b squared. So then this means that considering this, and that they are equal, we can conclude that 1 is congruent to 0 modulo 3, which is clearly a contradiction. Yes, because 1 minus 0 is 1, and 1 is not divisible by this. So that is a contradiction. Okay, so this means that this contradiction comes from this fact that I assume that this is not the case, and I assume that 3 doesn't divide B. So if 3 doesn't divide B, I come to a contradiction, so it means that 3 has to divide B. It means that B is divisible by 3. Okay? Okay, so now we finally finalize this problem by proving statement number 4 based on the previous statements that we have proven so far. Okay, we want to prove that square root of 2 plus square root of 3 is irrational. I start proving this using proof by contradiction. Yes, so what should I write? I would say that assume that this is not the case, and square root of 2 plus square root of 3 is rational. Therefore, there exist positive integers a and b such that square root of 2 plus square root of 3 is a over b, and the greatest common divisor of a and b is equal to 1. Yes? So this is not a loss of generality, because when you say that the square root of 2 plus the square root of 3 is a rational number, definitely it means that it can be written as a fraction whose numerator and denominator are integers. Yes? And assuming that these integers are positive is also not a loss of generality, because the square root of 2 plus the square root of 3 is a positive number. So either both of them should be positive or both of them should be negative. If both of them are negative, I cancel the negative signs, then I rename those. Then I come to a fraction with positive numerator and denominator. This is not also a loss of generality. Why? Because assume that a and b has some other factor except 1 in common. Then what can I do? I can just simplify the numerator and the denominator of that fraction by that common divisor, by that common factor, and then I can continue this simplification until I come to a fraction which is irreducible. It means that I cannot simplify it more. In that case, the numerator of that fraction, I call it a. The denominator of that fraction, I call it b. So this is also not something that can always be assumed. Okay? Okay, now let us see how it goes. In statement number 3, we learned that if square root of 2 plus square root of 3 is a over b, so statement number 3 gives me that a to the 4 plus b to the 4 is equal to 10a squared b squared. Yes. So we know that this is the case. Okay, but on the other hand, just look at this fraction. This fraction gives us a pair of integers a and b. For the time being, don't consider this. Consider only a and b. For this pair of integers, I have 4 possibilities. Okay, what are those possibilities? So let me write it here. Either both of them are divisible by 3, or 3 is divisible by a is divisible by 3, but b is not divisible by 3, or a is not divisible by 3, but b is divisible by 3, and finally none of them is divisible by 3. Yes? This is completely clear. If I have a pair of integers, at least one of these cases should be correct. Yes? So let me write something here, or this, or this. Okay? Okay, now let us consider this into account. Because the greatest common divisor of a and b is supposed to be equal to 1, so this means that this cannot happen. Yes? So I need to rule this out, because if a and b are simultaneously divisible by 3, then the greatest common divisor of a and b is at least 3, not equal to 1. So this cannot happen. So remember, on the one hand, one of these cases should happen. On the other hand, we realize that the first option should be ruled out. It's not possible. The second one also should be ruled out. Why? Because of statement number 4. Statement number 4 tells you that if A is divisible by 3, then B is also divisible by 3. So this means that I have to rule this possibility out. This cannot happen. Similarly, because this expression is symmetric with respect to A and B, if I change A to B, B to A, nothing will change here. So exactly I can write another statement that if B is divisible by 3, then A is also divisible by 3. It's immediately clear that I can prove such a thing. So this means that this is also not possible, and I have to rule it out. Okay? The only possibility which is left is that the last one. So 3, A is not divisible by 3, B is not divisible by 3. But this is also not possible. I want to show that the last one is also not possible. Then it means that I have a contradiction, because on the one hand, I should have at least one of these cases. On the other hand, none of these cases can be true. So it means that I have a contradiction. This contradiction comes from the fact that I'm assuming that the square root of 2 plus the square root of 3 is rational. So this means that this is not the case, and the square root of 2 plus the square root of 3 should be irrational, and then I am done. So the only thing that is left for me to do is to show that this cannot work here. Okay? Let us see why. Let us assume that 3 doesn't divide it. A is not divisible by 3. So do you remember, what does it mean? By statement number 1, we have A is equal to 3k plus or minus 1. Again, this means that A is congruent to plus or minus 1, yes, modulo 3. And then if B is not divisible by 3, then again, based on a statement number 1, B is also 3 times some k prime, for example, plus or minus 1. Then it means that B is also congruent to plus or minus 1 modulo 3. Yes, so by raising to power 2 here, I will get this is congruent to 1, A squared is congruent to 1 modulo 3, and A4 is also congruent to 1 modulo 3, and the same thing here. B2 is congruent to 1 modulo 3, B4 is also congruent to 1 modulo 3. Okay? Okay, but what we know, so from here and here, from this one and this one, if I add both sides together, I will get A4 plus B4 is congruent to 2, yes? Modulo 3. If I add both sides. And now let us see what happens here. 10A squared B squared is congruent to, if I want to simplify this modulo 3. A squared is 1 modulo 3. B squared is also 1 modulo 3. But 10 is also 1 modulo 3. Yes, 10 is congruent to 1 modulo 3. Why? Because if 10 minus 1 is 9, and 9 is a number which is divisible by 3. So 10 is also congruent to 1 in modulo 3. So what can I write here? Instead of 10, I can write 1. Instead of A squared, I can again write 1. And instead of B squared, I can write 1 again. And then if I simplify this, 1 times 1 times 1 is 1. Yes? So A to the 4 plus B to the 4 under this condition is congruent to 2 modulo 3. And 10A squared B squared under this condition is congruent to 1 modulo 3. On the other hand, these two numbers are supposed to be equal. So then what does it mean? It means that I have to admit that 2 is congruent to 1 modulo 3, yes? Because these two numbers are exactly the same numbers. One of them is congruent to 2, the other one is congruent to 1, so it means that 2 and 1 should be congruent to each other modulo 3. But this is also a contradiction, yes, because 2 minus 1 is 1, and 1 is not divisible by 3. So this is also a contradiction. So let me write it with red. Contradiction. Yes. Okay, so actually we are done. So just let me tell you something. So when I write square root of 2 plus square root of 3 is a over b, a and b is a pair of integers, so at least one of these cases should be valid. Yes, these are the only possibilities. But I showed that based on what we have done so far in the previous statements, all of these possibilities cannot happen. So I have to rule out all of these possibilities on one hand. On the other hand, these are the only possibilities available. So it means that this cannot happen, and that's a contradiction. So finally this contradiction here comes from the fact that I assume that the square root of 2 plus the square root of 3 is rational. So it means that this is not working. It gives rise to a contradiction. So the opposite one is the negation is actually correct, and that is the square root of 2 plus the square root of 3 is irrational. Okay, now we go to the second part of the problem. We want to prove that the square root of 6 plus the square root of 7 is an irrational number, and it is given us in the problem itself that we need to consider divisibility by 5 instead of divisibility by 3. Okay. Okay, so let us see that how we should modify each one of these statements. Okay, if we want to consider divisibility of 5, okay? Divisibility by 5. So if you remember, I told you that if n is an integer, and if m is a natural number, then the division algorithm asserts that there exists a unique q in Z, and there exists a unique r in Z, such that n is equal to mq plus r, and r is in this interval, yes, between 0 and m. Okay, now let us replace n with a, and let us replace m with 5 this time. Yes, then it means that I can write a as 5q plus r, and then r is in this interval between 0 and 5. Yes, okay, r is between 0 and 5, and then r belongs to the set of integers. Then it means that r is 0, 1, 2, 3, or at most 4. Okay. Okay, so if r is equal to 0, then a becomes equal to 5q. If r is equal to 1, then a becomes equal to 5q plus 1. R is equal to 2, a becomes 5q plus 2. R3, a becomes 5q plus 3. And finally R4, a is 5q plus 4. Yes. Okay, now again here, do you remember in statement number 1, a assumed to be not divisible by 3. So now let us assume that a is not divisible by, let me write it here, a is not divisible by 5. If a is not divisible, if 5 doesn't divide a, then this cannot happen, not acceptable in this case. Yes, but there are 4 possibilities left for us now. One of these possibilities. Okay, but let me write it in a little bit modified way that becomes similar to statement number 1 given in the problem itself. Okay, so what can I do? I can write it like this. Here I can write 5q, instead of 4 I can write 5 minus 1, then I can factor 5 from the first 2 terms, and then I have minus 1. I can call this k, so it becomes 5k minus 1. Yes, so if I consider this one, first one, and this last one, it means that a is a multiple, integer multiple of 5, either plus 1 or negative 1. Okay, and the same thing happens more or less similar here. So here I can write it 5q plus, instead of 3 I can write 5 minus 2. Then I can factor 5 out from the first 2 terms. Then I will have this minus 2. And if I call this 1k, then it becomes 5k minus 2. Okay, so what does it mean? It means that if a is not a multiple of 5, if a is not divisible by 5, then a is multiple of 5 plus 1 or minus 1, or multiple of 5 plus 2 minus 2. Yes, so the bottom line is that if a is not divisible by 5, then there exists a k in Z such that a is equal to 5k plus or minus 1, or a is equal to 5k plus and minus 2. So that is statement number 1. This is the analog of statement number 1 if I want to consider divisibility of 5 instead of divisibility by 3. Okay? Okay, so let me modify this last statement a little bit. So if I have a equals 5k plus or minus 1, this means that a is congruent to plus or minus 1 modulo 5. Yes. And if a is equal to 5k plus and minus 2, then this means that a is congruent to plus or minus 2 modulo 5. Yes. Here, if I raise this one to power 2, both sides, this a squared becomes congruent to positive 1 modulo 5. And then if I raise it once more, then I will get a to the 4 is also congruent to 1 modulo 5. Yes. So yeah, these are the cases that might happen if I write this in the language of congruency. Yes. Of course, these are all under the condition that a is not divisible by 5. And then if this happens, let us see what's going on. If I raise it to power 2, then it becomes 4, because it doesn't matter. Plus or minus 2 to the power of 2 becomes positive 4. Okay, but then 4 can also be written as minus 1 when I am working in modulo 5. Yes, so a to the 4, a to the 2 is minus 1. Yes, so let me put this in a box. The reason for the last statement is that 4 is congruent to minus 1 modulo 5. The reason is that 4 minus minus 1 is positive 5, and 5 is divisible by the module. Yes. And then if I raise both sides to power 2 once more, then a to the 4 becomes again 1 modulo 5. Yes. So what you see is that if a is not divisible by 5, for a I have 4 possibilities in module 5. Plus or minus 1, plus or minus 2. But for a squared, I have 2 possibilities. Yes, plus 1, minus 1. But for A4, I have only one possibility, and that is always equal to 1. Yes. So let me just summarize this here with a little different color. So if 5 does not divide A, meaning A is not divisible by 5, then A itself is congruent to plus or minus 1 or plus or minus 2 modulo 5, and A to the 2 is congruent to plus or minus 1 modulo 5, and finally A to the 4 is always congruent to 1 modulo 5. Yes. So this is what we will need for the next part of the problem. Okay, so let me go to the next part now. This is something that I will use later. Okay, now our goal is to prove that square root of 6 plus square root of 7 is actually an irrational number. Okay, so let us see how much space do I have here. Okay, for the next part is enough. So let me write this here. Our goal is to prove that square root of 6 plus square root of 7 is an irrational number. Assume that this is not the case. This is not the case, and square root of 6 plus square root of 7 is rational. Okay, so what's the meaning? Therefore, there exist integers, positive integers such that square root of 6 plus square root of 7 is a over b, where the GCD of a and b is equal to 1. It means that the only common factor between a and b is 1. Okay? Okay, and now I start from this statement: square root of 6 plus square root of 7 is a over b. Then I raise both sides to power 2. It becomes the first one to the 2 times the first one times the second one. The second one to the 2 is a squared b squared. And then 6 plus 7 is 13. I move it to the right hand side. It becomes a squared over b squared minus 13. To get rid of the final square root sign, I raise both sides to power 2 once more. The left hand side is 4 times 42, which gives me 168. On the right hand side, the first one to the 2 is a to the 4, b to the 4, minus 2 times the first one times the second one, and then finally the second one to the 2, which is 169. Okay, and then what I do, I multiply both sides by b to the 4, so it becomes 168b4. On the right hand side, I will have a4 minus 26a squared b squared, and then finally 169 b to the 4. Okay, and then you can see that I can move this to the left hand side, make it positive, move this term to the right hand side, make it negative. 169 b4 minus 168 b4 becomes just b4. So simply I will get a4 plus b4 is equal to 26a squared b squared. So look, I assume that square root of 6 plus square root of 7 is irrational. On the contrary, then I came to this conclusion that there should be two positive integers a and b whose GCD is 1, and then they fulfill this condition that a to the 4 plus b to the 4 equals to 26 times a squared b squared. Okay? Now I want to go, this is analog, this what you see here is the analog of this expression, yes, in the previous case. Now I want to prove statement something similar to this, but for divisibility by 5 instead of 3, yes? So I want to prove that if a is divisible by 5, then b is also divisible by 5. So that's my goal, okay? So let me go to the next page. Let me write my goal. My goal is to prove that, so what we got is that a to the 4 plus b to the 4 is equal to 26a squared b squared, you remember? Now my goal is this. Let me change my color. I want to prove that if a is divisible by 5, meaning that 5 divides a, I want to prove that 5 also divides b. b is also divisible by 5. I can prove this part by contradiction, by proof by contradiction, yes? So how? Let me write it down here. Assume that this is not the case, and assume that this is not the case, and 5 doesn't divide b. Okay? Now let us see, of course we are assuming that 5 divides a, but I am assuming on the contrary that 5 does not divide b, and I want to come to a contradiction, okay? So what I have, if 5 does not divide b, let me go to the previous page, and then you see that here, I have written it here. If a number a is not divisible by 5, its square can be written as plus or minus 1 if I am working in module 5, but its fourth power is always congruent to 1 in module 5, yes? Okay, so what I know is that if 5 does not divide b, I realize that b to the 4 is congruent to 1 module 5. Yes? On the other hand, I know that a is divisible by 5. Okay, so what does it mean? 5 divides a, it means that a is congruent to 0 in that module. So if I raise it to power 4, then it becomes a4 is congruent to 0 module 5. And then if I add these two side by side, then I will get a to the 4 plus b to the 4 is congruent to 1 plus 0, which becomes 1 module 5. Yes? On the other hand, because a is congruent to 0 to the power in module 5, then I can raise both sides to power 2, and then multiply both sides by 26b squared. Then what I get is this. It becomes 26a squared b squared, and on the right hand side I will have 0 module 5. Yes? Okay, so let me consider these. So I consider this number 1, consider this number 2, and number 3. Yes? I know that a4 plus b4 is congruent to 1. I know that this expression is congruent to 0. And on the other hand, I know that these two numbers are the same. So this means that if I use 1, 2, and 3, this will imply that 1 is congruent to 0 modulo 5. Yes? Because this one is congruent to 1, this one is congruent to 0. On the other hand, these two numbers are the same, so I have to come to this conclusion that y is congruent to 0 modulo 5, which is a trivial, which is apparently a contradiction, yes? So let me write this here. This is contradiction. Yes? Because 1 minus 0 is 1 and 1 is not divisible by 5. So if I assume that b is not divisible by 5, I come to a contradiction. So it means that I have to assume that this is correct. And then I am done. Okay. Now we want to go to the final step here, and we want to prove that square root of 6 plus square root of 7 is indeed irrational. Okay, we realize that if this is not the case, do you remember? Here I wrote that, assume that this is not the case, and this is rational. So I put it in equal to a over b, and I got this one. Okay, so let me just write this again here for you. So we know that square root of 6 plus square root of 7 is a over b. We know that the GCD, greatest common divisor of a and b, is equal to 1. And we realize that a to the 4 plus b to the 4 is 26a squared b squared. This is what we have so far. On the other hand, a and b is just a pair of integers, positive integers. Okay, so it means that one of these conditions should hold. Yes, which conditions? I would write them here for you. Either 5 is divisible, a is divisible by 5, and b is also divisible by 5. Either this should happen, or 5 is divisible, a is divisible by 5, but b is not divisible by 5, or the other way around, a is not divisible by 5, but b is divisible by 5, and finally, both of them are not divisible by 5. Yes? Because I have two numbers, a and b, they are integers, at least one of these, so exactly one of these should hold, yes? There are no other options available for a pair of numbers a and b with respect to the divisibility by 5. Okay? But I want to show that all of them give rise to contradiction. Okay, so it means that it is not possible to have one of them. So let me repeat. On the one hand, we have to have one of them. On the other hand, assuming each one of them will give rise to some contradiction. So it means that the whole thing is a contradiction, and the contradiction comes from the fact that I am assuming that this is rational. So it means that it is not rational. Okay, so let us see what I am doing here. So you see here I have GCD of a and b is equal to 1. So it means that they don't have any positive factor in common except 1. So this means that I can rule this out. This should be ruled out. This is not possible under these circumstances. Yes? If both a and b are divisible by 5, it means that the GCD of a and b is at least 5, not equal to 1. So I have to rule this out. I also rule this second one out. Why? We just prove it here. Do you remember? If 5 divides a, we learn that 5 has to divide b as well. So if 5 divides a, this cannot happen simultaneously. So I can rule this one out. And the same scenario is exactly going on here. Yes? Because this argument, this expression here is completely symmetric with respect to a and b. I don't need to go through it again. I just rename A to B, B to A everywhere in these arguments up to here. And then I will have the proof that if 5 divides B, 5 also should divide A. Exactly similar. So this is also not happening. So I have to rule this one out. And then there is only one thing left. I want to show that the last statement, that this last statement also is not working here. Why? The answer is simple. Okay, so if 5 does not divide A, yes, let me go back to the previous page to show it for you. So you see, if A is not a multiple of 5, then A squared is congruent to plus or minus 1, and A to the 4 is only congruent to 1. Okay, let me write them here for you. So then this means that A squared is congruent to plus or minus 1 module 5, and A to the 4 is congruent to 1 module 5. The same thing happens if 5 doesn't divide B. So this means that B squared is congruent to plus or minus 1 modulo 5, and B to the 4 is congruent to 1 modulo 5. Okay, but then from here, A to the 4 plus B to the 4 is congruent to 1 plus 1 module 5, so I am adding both sides of this. Then what I get is that A to the 4 plus B to the 4 is congruent to 2 module 5, so let us keep it. Okay, but then what can I do for the right hand side, 26A squared B squared? So let me simplify this expression. So when A squared is congruent to plus or minus, let me not write a lot. So here, what I want to do is to multiply both sides of these congruency relations. Then what I get is that A squared B squared is congruent. Plus 1 multiplied by plus 1 is plus 1, plus times minus 1, minus 1 plus times 1, they are minus 1, minus 1 times minus 1. So it means that at the end, again, I will have plus or minus 1 modulo 5. Yes? But on the other hand, I know that 26 is also congruent to 1 modulo 5. Yes? Why is that? Because 26 minus 1 is 25, and 25 is divisible by 5. So that's also a correct statement. Now it means, now if I multiply these two, what I get is this. I get 26 A squared B squared is congruent to plus or minus 1 modulo 5. Yes? But on the other hand, so let me call it number 4, 5, yes, and then I have relation number 1 again as before. So now using 1, 4, and 5, what I get is that 2 has to be congruent to plus or minus 1 module 5. But none of them actually can happen, yes. So 2 congruent 1 module 5 is completely false, yes, because 2 minus 1 is 1 and 1 is not divisible by 5. 2 congruent minus 1 module 5, this is also false because 2 minus minus 1 is 3 and 3 is not divisible by 5. So both of them are actually false statements, so this is my contradiction. Okay, so this means that I have to rule out this one as well. So on the one hand, A and B are a pair of integers. They should satisfy exactly one of these statements. But each one of these statements gives rise to a contradiction, so it cannot happen. So it means that assuming that this number is rational gives rise to contradiction in all possible cases. So this means that this cannot happen. So the negation of this statement, which means that the square root of 6 plus the square root of 7 is irrational, should be true. Yes? Okay, now we are ready to answer the last part of this problem. Why can divisibility by 3 not be used in this case? Okay, assume that you want to use the divisibility by 3. So let me just remind you of what we have so far. We learned that if 3 does not divide a, then a is 3k plus or minus 1 for some integer k. Then we realize that a becomes congruent to plus or minus 1 modulo 3, and then this means that a to the 2 is congruent to 1 modulo 3, and this also means that a to the 4 is also congruent to 1 modulo 3. Yes. Okay, now assume that you want to solve this the second part problem based on divisibility by 3. Yes, so what you do then? You do the same thing. You would write, okay, let square root of 6 plus square root of 7 be a over b, where a and b are positive integers and the greater common divisor of a and b is equal to 1. And then you continue again as before, and then you get a to the 4 plus b to the 4 is equal to 26a squared b squared, as we have done so far. And then you want to come to a contradiction. Yes, so it means that then I will have 4 possibilities. 3 divides a if I want to do everything based on divisibility by 3. So the cases that I would need to consider and rule out would be these cases. The first case, 3 divides a, but 3 does not divide b, and then 3 does not divide a, but 3 divides b, and finally 3 doesn't divide a, and 3 doesn't divide b. Yes. What I'm trying to say is that again you will be able to rule out the first 3 but not the last one. Okay, so I don't want to, for example, this you immediately can rule out again. The reason is that the greater common divisor of a and b is supposed to be 1. If this is going to be the case, then the greatest common divisor between a and b should be at least 3. Okay, but this one you can also rule out. But this time you need to use this expression. Yes, and that is easier in this case because a4 is congruent to 1, and then the same scenario, b4 would also be congruent to okay, if you want to prove this, by the way, you need to prove this by contradiction once more. But let me try just answer the question, not make it so long. I want to show that you will not be able to rule this last possibility out if you still insist to work with divisibility by 3. Okay, if you want to see why you can rule this out, you need to show that again if 3 divides a, then 3 also divides b, but this time you need to make use of this expression instead of the previous one. Okay, so this is easy, and then you can prove this again by contradiction as I did before. Okay, so this is easy, this is easy. So it means that you can immediately rule all of these out, but not the last one. Why this is the case? Let us check. If 3 does not divide a, then what I will get that a to the 4 is congruent to 1 modulo 3, and then if 3 does not divide b, b4 is also congruent to 1 modulo 3, But then if I add them side by side, it becomes a to the 4 plus b to the 4 is congruent to 2 modulo 3 on the one hand. But now, let me calculate the second one. So 26 itself is congruent to 2 modulo 3, yes? Why? Because 26 minus 2 is 24, and 24 is divisible by 3. So this is a true statement. On the other hand, a squared is congruent to 1 modulo 3. Here we have it, you see. And the same thing for b, yes? b squared would be also congruent to 1 modulo 3. So if I multiply all of them side by side, then I will get 26 a squared b squared is congruent to 2 times 1 times 1 modulo 3. So then it means that I have 26 a squared b squared is congruent to 2 modulo 3. But you see, this is no longer a contradiction. It might happen, yes, because this number is equal to this number, yes, because of this expression we have. But both of them, of course, are congruent to 2. So this is not a contradiction. So if I want to compare them, what I get is that 2 is congruent to 2 modulo 3, which is, of course, true, not a contradiction. Not a contradiction. So this means that if you still insist to continue with the divisibility of 3 instead of 5, everything seems okay except the last one. You are not able to rule this one out.